your headphones because AudioX is here to shake up the world of anything to audio generation. At its core, AudioX is like the ultimate audio wizard, taking in text, video, images, even existing music, and whipping up high-quality audio with Diffusion Transformers. Instead of struggling with isolated models for text to audio, video to audio, or music completion, AudioX unifies them all into one sleek system. And its secret sauce? Multi-modal masking. Stick around as we are diving into it.
First, let's talk about why audio and music generation can be so challenging. One big issue is that many existing models work in silos. Each one is specialized to handle just one type of input, like text or video, but not both. They're also limited by the amount of high-quality training data available, and they often struggle to integrate different kinds of inputs in a meaningful way. This work introduces a new model called AudioX, short for Diffusion Transformer for anything to audio generation. It can generate both audio and music using a single, unified approach. Unlike previous methods that are domain-specific, AudioX takes multiple input types, text, video, images, music, audio, and learns from them all. The core trick is a multi-modal masked training strategy. Parts of the inputs are hidden so that the model is forced to uncover relationships across different modalities. That makes it more robust and flexible when creating sound. Because good data is hard to come by, the authors built two new datasets to train and test AudioX. The first is VGG Sound Caps, with 190K audio captions based on the VGG Sound dataset. The second is V2M Caps, which boasts 6 million music captions derived from something called V2M. Look at the radar chart in the paper to see how well AudioX performs across different tasks. This chart uses inception scores to visualize quality and diversity. The model not only competes with specialized systems in various tasks, but often surpasses them. Why does this matter? This AudioX points to a future where a single model can handle just about any scenario, text prompts, videos, images, or even other audio. And with the code and data promised for release, it's an exciting leap forward for anyone working on automated audio generation. Let's dig deeper into how audio generation fits into the broader multimedia scene. High-quality audio is crucial for capturing attention and stirring emotions in social media, films, and video games. But producing great sound can be expensive and time-consuming, so automating it has become a major research goal. Right now, many models can generate audio, but most still accept only one type of input. Some are exclusively text-to-audio, others are video-to-audio. Fewer can deal with multiple inputs at the same time. The scarcity of large, high-quality data that covers these various input types is a big reason behind that limitation. AudioX addresses this by embracing an anything-to-audio mindset. It's designed to accept text, video, images, or even other audio, and then produce coherent sound. That's made possible by two new large-scale datasets. One with 190,000 audio captions from VGG Sound, and another with 6 million music captions from V2M. And at its core, it uses a transformer-based model that integrates diffusion processes to generate high-fidelity audio. If you're familiar with diffusion models in image generation, this is a similar approach but adapted for sound. A clever twist is that the training uses masking, so some parts of the input get hidden. That forces the model to really learn patterns that apply across different modes of data. The end result is a single system that can switch between tasks, text to audio, video to audio, or any other combination, without needing separate, specialized pipelines. In short, AudioX moves multimodal learning forward by combining transformers, diffusion methods, new datasets, and a masked learning strategy. The authors benchmark it against other state-of-the-art models and find that it either matches or outperforms them on various metrics. The aim is a single, powerful framework that can turn any media input into high-quality sound. Now, you might be wondering how AudioX compares to other generative audio models. Most current systems focus on a single scenario, like turning text into environmental sounds, or performing music generation from text prompts. Others handle tasks like audio inpainting, filling in missing sections of sound, or aligning audio with video for special effects. Some even combine text and video hints. But overall, these models are still pretty constrained. The goal here is to go beyond those limits with a unified approach. AudioX integrates text, video, image, and audio into one architecture, rather than training separate models for each. A big part of making that work is automated caption generation. Check out the figure in the paper to see how the process looks. The authors use something called Qifeng audio to generate text descriptions for different types of audio data. For general video audio clips, Qifeng audio outputs natural language descriptions, like train passing with whistle sound. For music clips, it gives more structured labels: genre, instruments, mood, tempo, and so on. This automatic labeling matters because it creates better training data. A lot of existing datasets don't come with detailed annotations, which makes training more challenging. By applying Qifeng audio to large datasets, the authors can produce rich text labels that significantly improve the model's understanding of the audio. They also apply a masking strategy, similar to what's used in text models like BERT, but here it's applied to audio and music. Parts of the sound are hidden, and the model learns to fill those gaps based on the remaining context. The idea is to encourage the system to develop more robust representations. Finally, the authors discuss how they crafted their dataset strategy. Many existing datasets focus on just text to audio or video to audio, but not both. So they augmented video datasets with audio descriptions, using Qifeng audio for automatic captions. This results in a much richer, more diverse dataset that can handle multiple modalities. By combining a unified model architecture, automated captioning, and sophisticated masking, AudioX paves the way for a multimodal audio generation system that's far more flexible than earlier methods. Curious how this all comes together to generate sound? The model handles multiple inputs, video, text, and audio through specialized encoders. But the twist is a random masking strategy. Have a look at the relevant figure here to see how different pieces get masked. Parts of the video frames, text tokens, or audio waveforms are hidden before encoding, which pushes the model to make stronger cross-modal connections. After each modality is encoded, they all land in a common representational space. Video embeddings go through a temporal transformer to capture how things change over time. Text and audio embeddings are handled through simpler linear transformations. Then everything is concatenated into one multimodal embedding that summarizes the overall input. Next, the system uses a diffusion transformer, DAT. If you recall, diffusion works by gradually adding noise to a signal, the forward process, and then learning to remove that noise, the reverse process, to restore the original data. It's been highly effective in image generation, and now it's adapted here for audio. Training requires pairs of inputs and the corresponding correct audio output. If a modality is missing, maybe there's no text or no video. The model uses placeholders like generate music for the video. In audio inpainting tasks, the model sees a piece of the audio blanked out and tries to restore it. The loss function is straightforward. It measures the gap between the noise that's actually added and the noise the model predicts, so the model gradually learns to generate realistic sound that fits the context. That's basically how AudioX handles text to audio, video to audio, or even partial audio to audio tasks. It's flexible because it uses a unified approach that can adapt to different inputs. Next, we'll take a peek at some real-world experiments to see how well it performs. Let's look at the overall pipeline in more detail. Check out the diagram here. You'll notice that each input video, text, and audio goes into its own encoder first. The visual encoder is fed frames at a rate of 5 frames per second to extract features over time. The text encoder converts sentences into meaningful embeddings, courtesy of a language model. Meanwhile, the audio encoder reconstructs audio from any existing sound input. The random masking happens first, so parts of each input are deliberately hidden. Then, after encoding, these embeddings get merged in a shared space and fed into the diffusion transformer, DIT. Unlike a normal transformer that just predicts the next token, DAT operates over multiple steps, slowly denoising the audio signal. The output then goes through the audio encoder to ensure that the sound is realistic and aligned with the inputs. This is a large model, over 2.4 billion parameters, with 1.1 billion of those being trainable. It's trained step by step, with careful tweaks to the learning rate to keep things stable. Multiple scoring approaches are used to judge the quality of the results, like perceptual audio tests and alignment metrics that check how well the generated sound matches the context. The takeaway is that AudioX isn't just tackling straightforward tasks like text to audio. It's doing so for multiple modalities and often outperforming earlier methods. Let's walk through some specific benchmarks to see how those metrics stack up. So how does this model measure up in practice? The paper looks at tasks like text to audio, T2A, video to audio, V2A, and text and video to audio, TV2A. The main question is whether the system can consistently generate audio that's both high quality and relevant to the given input. To judge that, the authors use several metrics. KL divergence checks how closely the generated audio follows real-world distributions. Inception score measures quality and diversity, while Frechet distance, or FD, and Frechet audio distance, or FAD, compare generated samples to actual audio. Production complexity, PC, and production quality, PQ, look at naturalness and the overall listening experience. Here's what happens. In text-to-audio tasks, AudioX sets the bar high with the lowest FD and FAD, indicating its outputs are especially close to genuine sounds. In video-to-audio, it still performs strongly, and even surpasses many baselines when it comes to aligning the sound with the video context. Then there's the text and video-to-audio scenario, and that's where AudioX really shines, combining the cues from both text and visual footage to create highly accurate results. It's also tested on music generation. In text-to-music, T2M, AudioX captures the feel of the text prompts very well. In video-to-music, V2M, some specialized models may still have slight advantages, but AudioX remains highly competitive. Overall, it's a system that adapts smoothly across different tasks, offering a solid balance of quality and flexibility. But that's not all. The model is evaluated on 3 more scenarios: audio in-painting, music completion, and image-to-audio generation. Why these tasks? Because they really show off how multimodal conditioning can step up performance. Take audio in-painting. The model needs to fill in missing segments, guided by whatever contextual input is available. If the only cue is text, the model does well enough. But when video is also present, things get even better. The FAD scores confirm that multimodal input leads to more accurate restorations. For music completion, the challenge is to extend a snippet of music in a way that stays true to the original. Results improve when you add text or video cues, and if you combine all 3, text, video, and partial music, you see the best performance. It's a clear sign that the model can effectively merge different streams of information. Then there's image-to-audio generation, where the task is to produce sound effects based on a still image. Compared to other methods like seeing and hearing or IM2Wave, AudioX strikes a strong balance between realism and alignment with the visual content. Finally, the paper describes a user study where people listen to samples for tasks like text-to-audio, video-to-audio, and video-to-music. Participants consistently preferred AudioX over the alternatives, both for quality and relevance. It's more evidence that a multimodal approach can outperform single-modality strategies in terms of user satisfaction. Now let's talk about how the model figures out the best way to learn from each input type. An ablation study checks different masking ratios for text, video, and audio. Look at Figure 5 to see these results. It turns out text benefits from a lower masking ratio, around 20%, because a little bit of missing text is enough to force better learning without stripping away too much context. Meanwhile, video and audio see bigger gains when up to 60% is masked, probably because there's more redundant data in those modalities. Then, if you glance at Figure 6, you'll find a comparison between the unified multimodal model and single-modality versions. The unified one wins by a significant margin, proving that pulling information from different sources really does boost learning. The right side of Figure 6 focuses on music generation and shows how performance goes up as more types of inputs, first text, then video, and finally both come into play. Putting it all together, this paper shows that masking strategies help the model learn better representations, and that multiple inputs create richer, more reliable audio generation. It's a step forward for intermodal learning and a demonstration that one model can handle a wide variety of audio generation tasks. That brings us to the end of this deep dive into AudioX. Thanks for joining us today. Happy exploring!